Hi, this is my project on dynamic depth speculative decoding with reinforcement learning. This project is motivated to accelerate LLM inference. LLMs run on expensive hardware, and with the recent trend, users demand more throughput for agentic workflows and long context reasoning. LLMs can be deployed to your local cloud. A bigger model is generally considered as more powerful, however, it also requires more compute to reach reasonable throughput for efficient serving. A widely used technique to speed up inference is speculative decoding. The insight behind speculative decoding is that some or even most tokens in a sequence are easy to predict, such as conjunctions, articles, propositions, or even certain keywords in the generated code syntax. Also, LLM responses might include repeated patterns from previous messages, which is also easy to predict. Thus, we can use a smaller model to predict those easier tokens and spend less compute and increase our throughput. To make this process lossless, we forward those n tokens predicted by the drafter model to the bigger model and verify them. The bigger model verifies whether it will have outputted the same tokens as those predictions. We take the longest continuous sequence of accepted tokens of the verifier. The generation process is generally memory bounded and the verification is compute bounded. In modern GPUs, trading off compute for memory is a good trade-off to increase throughput. This is a demonstration of the speculative decoding workflow. On the left, we have the bigger model with 16 layers, and on the right, we have the drafter model with only a couple layers. Here, the tokens in green are accepted and red are rejected. So the drafter model successfully predicted the next two tokens and saved us compute. The question is, how do we choose this drafting length n to maximize our throughput? If we keep n too long, we spend unnecessary time on drafting tokens that wouldn't be accepted. If we keep it too short, we miss opportunities to speed up generation by potentially accepted tokens. And studies show that the ideal n is context dependent. Based on prompt complexity, more or less tokens could be accepted on average. We formulate our MDP as a 6-dimensional vector with values between 0 and 1. We use the top 3 token probabilities outputted by drafter LLM. Previous study has shown those probabilities correspond with the drafter model's acceptance rate. Next, we have the current speculation depth, total sequence length, and our KV cache length to give us hints about the runtime of the next prediction. We take a look at the simplest form of speculation, a search tree of width 1. After each generated token, we use policy to decide whether to stop or keep generating more tokens using the drafter. We also have a fixed upper bound to prevent drafter from drafting infinitely. Finally, we have the reward. We use our optimization target, throughput, as the reward. Reward is only emitted when the episode is completed, where an episode is defined as drafting tokens and verifying it once. First, we tried an offline policy, Deep Q network. However, it got stuck in a safe policy, failed to explore, and find a good policy that beats even a simple baseline such as n equals 7. Second, the model became too conservative, feared to explore unknown paths, and refused to optimize further. And next, we tried PPO, a proximal policy optimization algorithm. It uses an estimated advantage function. However, the stochasticity of the drafting process caused the value function to fail distinguishing signal from noise. We only have stochastic state variables that tell us probabilities of some token being accepted. Therefore, for the same state, yielded rewards can be different, causing advantage estimation to fluctuate and fail. The collapsed advantage estimation failed the actor-critic loop and yielded 2 aggressive policies. Finally, we tried reinforce. We have experimented with different gamma values. A higher gamma resulted in a more aggressive policy, maximized rewards early on, but ends up being too greedy. A smaller gamma resulted in a more conservative policy, however the convergence took too long. An aggressive policy is associated with a deeper drafting length, taking more risks, whereas a conservative policy is associated with shallower drafting length, being risk-averse, as shown on the right. Second, we experimented with different batch sizes. When the batch size was too big, the gradient smoothed out. The stochastic signal got washed out, but the model also got stuck in a safer policy, yielding low rewards. A smaller batch size converged quickly without being stuck in local minimas. We have run 4 additional experiments to our reinforcement learning algorithms to form a good baseline. We have set n to be some constant number. This is the default approach in modern LLM inference. The y-axis is throughput, our objective. Higher the point, better it is. The x-axis shows the acceptance rate of proposed tokens. A higher acceptance rate means the model made more accurate or conservative predictions. A lower acceptance means the model made riskier predictions. We use two datasets. GSM-8K is a grade school math problem dataset, generally considered as easy to predict sequences because it consists of repetitive patterns while solving math problems. MT-Bench is a dataset to emulate multi-turn conversation, close to real LLM chat use cases. It consists of a combination of harder to predict tasks, such as creative writing. Our results show Reinforce outperformed all static baselines, with about 5% increase in throughput in both benchmarks. The optimal static policies form a Pareto frontier marked with a dashed blue line, fit into a curve. This curve shows an upper bound for static policies, meaning no fine-tuning on n can beat our reinforcement learning algorithm. Note that the optimal static policy for each benchmark differs. However, the reinforcement learning algorithm can dynamically adapt those changes, requiring no manual configuration based on workload. For PPO, the low acceptance rate shows a greedy approach, and for the deep Q network, the high acceptance rate implies the overly conservative policy. In this graph, the y-axis represents a unique prompt ID, sorted by throughput achieved using the RL policy. The blue dot represents the throughput achieved under the given static policy, and the yellow dot represents the throughput achieved under the RL policy. Samples to the right achieved better throughput. In this right, it's clear to see reinforcement learning algorithm beats the static policy for many prompts, only with a few exceptions. For example, for depth 4, the second graph, the widening gap higher y implies the static policy stopped too early, whereas reinforcement learning managed to squeeze out more throughput by dynamically adjusting the length. Similarly for depth 10, the first graph, the gap doesn't exist on higher y because it's a greedier policy, but instead the gap exists on lower y because the static policy greedily drafted too many draft tokens for low acceptance sequences, spending unnecessary time. Finally, each point in this graph is a single prompt, and the throughput difference between the given static policy and the reinforcement learning policy. Points to the left of the y-axis perceive better throughput under the static policy compared to the reinforcement learning policy. The reinforcement learning policy achieves better throughput for at least 80% of the prompts against the best static policy, showing strong signals of risk-aware decision making. Here are the references I used. Thank you.